Good morning, everyone. Welcome to the lecture series on operating system KCS 401. Myself, Rekha Baghel, Assistant Professor in Computer Science and Engineering Department, Ajay Kumar Garg, Engineering College, Ghaziabad. So, today's topic of this lecture is Semaphore. In this lecture, we will discuss the basic concepts of semaphore, the different types of semaphore, binary semaphore and counting semaphore. Two basic atomic operations, wait operation and signal operation. And next we will discuss some examples based on critical section problem. In the last we will discuss classical problems of process synchronization. So let's start with semaphore. So semaphore are integer variables, or we can say non-negative integer variable that acts as a signal. What do you mean by signal here? So semaphore acts as a signal. It means semaphore allow a process to get enter into the critical section or disallow a process to get enter into the critical section. So that's why semaphore act as a signal. So semaphore basically uses two types of atomic operations. First one is wait operation and second one is signal operation. A semaphore allows a process to enter into the critical section or disallow a process to enter into the critical section based on the value of the semaphore S. The value of the semaphore S is the number of units of the resources that are currently available. What do you mean by this one? Semaphore S is the number of units of the resources that are currently available. It means the initial value of the semaphore is the number of resources available at that moment. So this concept we can understand with the help of this example. What will be the initial value of the semaphore variable if there are 5 instances of the resource? For example, you can take the resource is a printer. 5 instances of the resource, it means 5 instances of the resource, it means 5 printers are available. So, 5 processes can access these 5 printers at a time. So, initial value of S is equal to 5 here. Okay. So, we can define semaphore variable, the value of the semaphore variable is the number of resources available at that moment. The two atomic operations can be performed on a semaphore, or we can say semaphore uses two atomic operations, wait operation and signal operations. Wait operation, we can just mention the wait operation. We can also call wait operation as P function, sleep function, decrease or down operation. It means the wait operation is the semaphore operation that controls the entry of the process into the critical section. Whenever a process wants to enter into the critical section, the first step that it performs is the wait operation on the semaphore. So, wait operation, what does it do? So, wait operation is an atomic operation. Atomic operation means whenever, this wait operation is, in this wait operation, the semaphore is initialized by 1, is always initialized by 1. Okay. So, here the atomic means the variable on which read, modify or update happens at the same time with no process is allowed to enter into the critical section. That means no other process is allowed to update, modify or read the shared variable at that moment. That's why we use semaphore. So this wait operation is known as a decrease or down operation. It means whenever a process want to enter into the critical section, the first step that process perform is the wait operation. It means it decreases the value of the semaphore. Okay, and next one is, for example, this is the some code. Code means whenever a process want to enter into the critical section, that process must first execute the wait operation on this semaphore. After executing the critical section part, the process must execute this signal operation. We will discuss what is a signal operation in next slide. So, this is the basic assumptions, this is the basic functionality that every process must perform. Before entering into the critical section, the process must execute the wait operation. After completing the critical section task, the process must complete the signal operation. Okay. So, for example, this is the code. There is a process P. There is a process, one process is there. That process first execute the P operation. P operation means wait operation. Wait operation, the process, there are two processes, P1 and P2, and a semaphore S is there. P1 and P2 and semaphore S is there. Now, if semaphore S is initialized by 1, S is equal to 1. S is equal to 1. So, there are two processes P1 and P2 and S is initialized by 1. Now, suppose if P1 enters in its critical section, then the value of S becomes 0. As in this code, we have mentioned that whenever a process want to enter into the critical section, that means that process must execute the wait operation. In wait operation, we decrease the value of the semaphore by 1. Means this is the wait operation, and in this, the while S is equal to 0, S is equal to S minus 1. Means when the P1 enters in its critical section, then the value of semaphore is decreased by 1. Now, if P2 wants to enter in its critical section, then it will wait until S is greater than 0. This is a very important point, that a process can enter into the critical section if S is greater than 0. This is very important. If value of S is equal to 0 or less than 0, then other process will wait until the value of S becomes the greater than 0. So, now P2 process want to enter into its critical section, then it will wait until S is greater than 0. This can only happen when P1 finishes its critical section and call V operation on semaphore. So, one process that enter into the critical section first complete the wait operation, means it decreases the value of semaphore by 1, and after executing the critical section, that process must execute the signal operation. In signal operation, we increase the value of the semaphore by 1. Okay. So, this is the code. So, in this code, there is a one problem. While s is equal to 0 means, note that there is a semicolon after while the code get struck. Here while s is 0, because semicolon is there means while loop will executed infinitely until s is equal to 0. Okay. When the value of s, when this operation will perform, then this while we will get out from the while loop. So, next operation is signal operation. Signal operation is also known as V. In some questions, you have found a V symbol. Okay, V symbol is written for signal operation. In some time, we use wake up operation. In some places, they used increased or up operation for representing the signal operation. So, all these terminology represent the signal operation. So, once a process has exited the critical section, we must update the value of the semaphore. This is done for allowing the other processes to get into the critical section. Means if s is equal to 0, if s is equal to 0, that means no other process is allowed to enter into the critical section. After completing the critical section part, the weight of the signal operation performed. Signal operation just increase the value of semaphore by 1, means 0 plus 1 is equal to 1. Now, other process can enter into the critical section. So, types of semaphore. There are two types of semaphore. First is counting semaphore and second one is binary semaphore. Counting semaphore. Counting semaphore is a non-integer signaling mechanism that can take any integer value. And using the counting semaphore, we can coordinate access to resources, and here the semaphore count is the number of resources available. Semaphore count is the number of resources available. If the value of the semaphore is anywhere above 0, then process can access the critical section or shared resources. If the value of semaphore is greater than 0, okay, in counting semaphore, the value of s can be any non-negative integer variable, okay, or the value of s must be greater than 0. So, if the value of s is greater than 0, so any process can enter into the critical section, and in this counting section, in this counting semaphore, the s represent the number of resources available, or we can say instances of the resources available. Okay. So, if the value of the semaphore is anywhere above 0, then process can access the critical section or the shared resources. So, in previous lecture, we have discussed that what are the different types of shared resources. So, shared resources can be a file, can be a common shared variable, can be some common input-output device. So, number of processes that can access the resource or code is the value of the semaphore. However, if the value is 0, it means there are not any resources that are available, or the critical section is already being accessed by the number of processes and cannot be accessed by more processes. So, we can define if s is equal to initially the value of s. If s is equal to 0, it means critical section is not critical section is not available, or we can say resource is not available. Okay. So, critical section in this semaphore, counting semaphore, S represents the number of resources, number of instances of the resource available at that moment. If value of S is 0, it means no resource is available at that moment. Counting semaphore, in this, by this, suppose if initial value of S, if initial value of S is greater than 0, that means resource is available. If some process acquires some resource, that means count, initially count in this count is equal to, initially the value of count, initial value of count is 0. Initial value of count is 0. If initial count is greater than 0, it means resource is available. If some process acquire the resource, then count is equal to count minus 1. Here the count initial value of this one, count is equal to number of resources available, number of instances of resource available. So, suppose n is equal to, here count means number of instances of the resource available. So, count is equal to sub 5, means total 5. Count is equal to 5 means total 5 instances of the resource is available. If for getting into the critical section, first it will check what the value of the count. If count is greater than 0, then wait operation will perform. Wait operation means the value of semaphore will decrease by 1, means count is equal to count minus 1. If process completed the critical section part, then signal operation will perform. Signal operation increase the value of the semaphore by 1, means count is equal to count plus 1, because resource is free by the process. If count is equal to 1, means count is equal to 1 means process release the resource, and count is equal to 0 means process acquire the resource. In this, this is the case of binary semaphore. So, we will discuss binary semaphore. So, in counting semaphores are generally used when the number of instances of a resource are more than 1 and multiple resources can access the processes. So, in this case, there are count is equal to 5 means there are 5 instances of the resource is available and 5 processes can access these 5 instances of the resource simultaneously. Binary semaphore. Next is binary semaphore. Binary semaphore, when a process is using the critical section of the code, we change the semaphore value to 0, and when a process is not using it, we can allow a process to access the critical section, or we change the value of semaphore to 1. So, in binary semaphore, the semaphore is the integer value that can only be 0 or 1. In binary semaphore, in counting semaphore, the value of S can be any value that is greater than 1. So, in counting semaphore, the value of S can be any non-negative integer value. But in binary semaphore, the value of S can be 0 or 1. So, in binary semaphore, the value can be 0 or 1. If the value of the semaphore is 1, it means that the process can proceed to the critical section. If the value of semaphore S is equal to 1, it means resource is available. Resource is available. If the value of semaphore is 0, it means not available. It means not available. Okay. If the value of semaphore S is equal to 1, it means resource is available. If the value of S is equal to 0, it means resource is not available. So, if the value of binary semaphore is 0, then the other process cannot continue to the critical section of the code. So, in this example, if we will check the value of the semaphore. So, initially the value of semaphore is 1. So, any process that want to enter into the critical section, first check the initial value of the semaphore. Here the value of S is 1, that means process is allowed to enter into the critical section, and the process will apply the wait operation on this semaphore. Now, after applying the wait operation, that means when the process using the semaphore for the wait operation, it will decrease the value of semaphore by 1, means now the value of semaphore is 0. It means when the value of S is equal to 0, it means the source is not available. The process cannot enter into the critical section by checking the value of S. So, if S is equal to value of S is, if the value of S is 0, it means resource is not available. If the value of S is 1, that means resource is available or process can enter into the critical section. So, there are two important parts, means whenever the process want to enter into the critical section, first it will check the value of S. If it is greater than 0, in case of counting semaphore, then it will enter into the critical section. So, how many processes can enter into the critical section in counting semaphore? Depends on the instances of the resources available. In binary semaphore, whenever a process want to enter into the critical section, it will check the value of S. If it is 1, then process can enter into the critical section. Then other process that want to enter into the critical section checks the value of S. Now, the value of S is 0, because after entering into the critical section, the first process applies the wait operation on S. That means the value of S is now decreased by 1. Now value of S is 0. So, other process check the value of S. Now, value of S is 0. It means other process will wait till process 1 completes its execution. So, this is an example. Suppose at a particular time of computation, the value of counting semaphore is 10. The value of counting semaphore is 10. S is equal to 10 here. Then 12 P operations. 12 P operation and XV operation. What do you mean by P operation? P operation is weight operations. Total 12 weight operations are performed, and XV operation, V operation means X signal operation was performed on this semaphore. If the final value of semaphore is 7, then X will be. We need to find the what will be the value of X, means how many signal operations were performed at that moment. So, for this, here the value of counting semaphore S is equal to 10. S is equal to 10. It is given here. P operation, total weight operation performed, 12 weight operation were performed. V operation means total signal operation performed. Total signal operation performed is X. We need to figure out how many what is the value of X. So, final semaphore value. Finally, we reach the value of S is equal to 7. So, by using this figure, we will calculate the value of X. So, P operation also called a weight operation, and it decreased the value of S by 1. So, total P operation means total 12 operation performed. So, how much value we decrease? Means total 12. Means after initial value of a counting semaphore S is equal to 10, after 12 P operation are performed, S value became -2. Why this -2? Because S, initial value of S is 10 and we applies total 12 P operation. Total P operation means total 12 weight operation. Weight operation just decrease the value of S by 1. So, one weight operation decrease the value of S by 1. So, total here 12 operation performs, means we decrease the value of S by 12. Okay. So, what is the value of S? So, S is equal to -2. S is equal to -2 here. X, V operations are performed in this semaphore S. Now, final value of counting semaphore S is equal to 7. It is given, final value of S is equal to 7. So, X, total how many operations will performed? Means total V operation X plus S is equal to final value. Final value is here 7. Okay. So, X plus S, what's the value of S is here? -2 is equal to 7. Now, X minus 2 is equal to 7. X is equal to 7 plus 2, that means 9. So, this is the final value of X. X is equal to 9. So, in this way, we can calculate the value of P and V operations. So, these type of questions can be asked in any competitive exam. So, in this lecture, we have discussed the semaphore, binary semaphore, counting semaphore, weight operation and signal operation. So, in next lecture, we will have solve some further problems of critical section and we will discuss classical problem of process synchronization. So, thank you.